Okay, so here's a transformation going from polynomials of degree 2 to polynomials degree 2, and it's the same basis for both the domain and codomain. So it says find the matrix of the transformation, just sometimes they use the word representation, relative to this basis. So sometimes they say relative to this basis and this basis, but they're both the same basis for the domain and codomain. All right, so we always go and apply the transformation to the different basis vectors. So I'm going to do it on 1. So if I was to write 1 in terms of a0 plus a1t plus a2t squared, that would give me a0 is 1, a1 is 0, and a2 is 0. So this is a random transformation, so you just get to go plug those numbers into here. And so I see I get 3. And then a 5t. And so it's my job to write that as a vector in terms of these 3 basis vectors, because those are the codomain. So I'd have 3, 5, and 0. All right, so now I get to go apply the transformation to t. So if I was to, again, write t as this would give me a sub 0 is 0, a sub 1 is 1, and a sub 2 is 0. So I use these 3 numbers into this formula here. So I would get negative 2t plus a 4t squared. So writing this as a vector, I'd get 0, negative 2, and 4. So last one, taking t squared. So rewriting t squared in terms of this, I get a sub 0 is 0, a sub 1 is 0, and a sub 2 is 1. So using these 3 numbers into this formula here, I would get t squared. A little unusual. So what does that give me? It gives me 0, 0, 1. So the matrix for the transformation would be 3, 5, 0, 0, negative 2, 4, and then 0, 0, 1. And that's all they wanted me to do in that problem. Okay, so here we're taking a transformation from polynomials up to degree 2 into R3. Okay, so let's apply the transformation to this polynomial. So what this means is for the first entry, I'm putting negative 1 in for t, so I can see 5 minus 3 is 2. For the second entry, I'm putting 0 in for t, so I get 5. For the third entry, I'm putting 1 in for t, so I get 8. So that's what the image of this polynomial is. Okay, so finding if it's a transformation, so remember t of p plus q. So applying this transformation, which means I'm going to have p plus q, all evaluating it at negative 1, p plus q at 0, and p plus q at 1. And so I use what I know about addition. So this turns into p of negative 1 plus q of negative 1, p of 0 plus q of 0, p of 1 plus q of 1. And I can break that up into p of negative 1, p of 0, p of 1, plus, right, because this is just using what I know about what happens with vectors, q of 1. So this is equal to apply the transformation to p and apply the transformation to q. Okay, that's number 1. So the second criteria is apply the transformation to cp. So I get c of p of negative 1, c of p of 0, and c of p of 1. And then I know I can factor a c out. And that is equal to the c times the transformation of t of p. Okay, here it is. Find the matrix for this these basis vectors for P2 into the standard basis for R3. So you know the standard basis for R3, whoops, is 1, 0, 0, 0, 1, 0, 0, 0, 1, right? So I've got to write it in terms of these three basis vectors. Okay, so if I apply the transformation to 1, so what that means is I'm plugging in, let me show it here, I'm plugging in a -1 for the t, a 0 for the t, and a 1 for the t. There's no t, so that means I get that vector, right? 1, 1, 1 in terms of the R3s. Okay, so that's pretty straightforward. Nothing to plug in. Okay, so this says for the first entry, I plug in -1 for t. There it is. Second entry, I plug in 0 for t. Third entry, I plug in 1 for t. All right, last one, t squared. So t squared, I plug in -1 for t, I get 1. Here I plug in 0 for t, I get 0. Here I plug in 1 for t, I get 1. So what's the matrix? The matrix M will be these three vectors.